This is a short clip to explain visually what you heard happening with the fire truck siren. So to start, we need something to compare to. So what this diagram represents is a non-moving or stationary source located right in the center here that is emitting sound waves at a regular frequency, an unchanging frequency. So we have 4 wavefronts that are spreading out from that source, just like how water ripples will spread out if you drop a rock in the pond. Yes, these are longitudinal waves, but we can still represent them with these wave fronts as if they were water waves, just as a way to visualize it, because it's very difficult to draw a longitudinal wave on a surface like this. The difference with the fire truck was that the source was moving. So what we see happening, that red circle is still in the center, and the source of these waves is moving towards the right-hand side of my screen. As it moves towards the right, it's still emitting those waves at a regular frequency. This started out as the same diagram as this, just with a couple more circles. What happens is as it's moving towards the observer, here you are, as it's moving towards the observer, that wavelength seems shorter because those waves are getting bunched up. The next one is emitted further to the right than the previous one, so there's not as much space in between them, and I get a wavelength that looks a lot shorter than my original one here. And if I think mathematically about this, V equals frequency times wavelength, I haven't changed anything about the medium, so the V needs to stay the same. If the wavelength appears to be lower, to get the same answer, my frequency needs to be higher. This would be like multiplying 3 times 4 to get 12, and then having that 4 shrink to 2. Now I have to multiply 6 times 2. So the frequency seems higher. And like we talked about the other day, frequency refers to the pitch or the note that you hear. I'm underlining the word seems because the frequency isn't actually higher. The driver is not doing anything different. There's not a different source, but because of that motion of the source, it appears to be higher for you. The same thing happens after the fire truck has passed you and it's moving away from you. Now the wavelength seems larger because as the source moves, those wavelengths are stretched out over more space. And by similar logic, now the frequency seems lower and I hear a lower pitch. Note that this is different than the volume. In that fire truck video, we do also hear changes in volume. As the truck gets closer to you, you do hear it louder. And as it gets away from you, you do hear it get quieter, but that's a separate conversation than the note you're hearing or the pitch. We can talk about the same kind of thing if instead of the source moving, we have the observer moving. This would be if something is sitting still and you're driving towards it and then driving away from it. I often hear this when I'm passing the bus stop. If the bus is playing the tones when it raises and lowers the floor of the bus or puts out a wheelchair ramp, I can hear this happening. If I'm moving towards these waves, that apparent velocity seems higher. From my perspective, I see those waves approaching me at a higher speed than what would be measured based on the medium. So by the same mathematical logic, this seems higher. The wavelength doesn't appear to change. They're still equally spaced here. So that means I would interpret or I would observe a higher frequency or a higher note. The same logic is true over here. From my perspective, because I'm moving off the screen to the right, it seems like the velocity is lower, the wave speed. So my frequency seems lower as a result. In terms of a general definition of the Doppler effect, I'm actually going to take the language straight from the Big Bang Theory clip that I put at the top of this Canvas page. The apparent changes in frequency because of the relative motion of the source and the observer. So the key word here is apparent. The horn or the beeping or the siren or whatever it is not actually changing its frequency. But because of the relative motion of the source and the observer, we observe something different. You could, I suppose, have a case where the source and the observer were moving at the same speed, and then you wouldn't notice anything. Now, this has more of an effect when that relative motion, I'm going to call this V, relative, is higher. This becomes more apparent the faster the source or the observer is moving relative to the other. The extreme case of the moving source is where we get sonic booms from. So this first picture is my object, my source, not moving at all like my first diagram. In the second one here, the velocity of that object, that pink source, is less than the speed of sound. And that's the case we were looking at with the fire truck. If that object is moving at something equal to the sound, all of these waves are compressed together. They can't get out of each other's way. So you have this massive buildup of pressure here, this shock wave that's emanating from that source as the air pressure goes from something normal to a sudden change that would be constructively interfering. So this is when we hear that sonic boom, when an object moves from this state to this state. It's this sudden pressure change in the air, and the shock wave travels outwards from that source as it breaks through the sound barrier. The volume of this really depends on the amount of air involved, which usually has to do with the size and the shape of the airplane. There's a lot of design and a lot of technical aspects that go into this. And below this video on the Canvas page, I'll put up some examples of where we hear this happening.